Hello everyone, my name is Fumio Machida from University of Tsukuba. Now I'm going to talk about Markov chain and Petri-nets for software rejuvenation systems. So this chapter was written by me and Professor Paolo Marcel in Federal University of Pernambuco. The purpose of this presentation is to introduce Chapter 5 of Handbook of Software Aging and Rejuvenation. So this chapter basically reviews the evolution of modeling studies on software rejuvenation systems. So we are going to present some recent advances in this research field as well, and also would like to discuss the future directions. As a beginning, so let me overview the content of this chapter. So this chapter is largely divided into two sections, Markov models and Petri-nets. Both of the two models are kind of state space models used extensively in the reliability study. So the initial model was given by continuous time Markov chain, CTMC. So it spawned two important research threads that we followed in this section. So let us quickly go through the history of these modeling studies together. So as you may have already studied in the previous chapters, the study of software aging and rejuvenation was originated by Fuan, Quintana, Coletis, and Fulton. So they developed the continuous time Markov chain, CTMC, to represent software aging phenomena. So the model is presented in this slide. The system states from robust state S0, so then goes to failure probable state represented by SP, and then goes to a failure state due to software aging. So once system enters failure state, the system tries to recover the system, and recover process completes, the system go back to robust state. So in this model, so all the state transitions are exponentially distributed time. So the resulting status model is continuous time Markov chain. So in the seminal paper, Fuan et al. Introduced a new state SR to represent the software rejuvenation state, so which is represented on the side of failure probable state SR. So now the state SP is a branch point. If there is no action in failure probable state, the system goes to fail due to software aging. But if any action, so which is software rejuvenation, the system goes to SR state and then recover to the system to robust state. So compared to system recovery after failure, software rejuvenation can be performed with less cost. Thus, we can reduce the downtime of the system. So the CTMC model analysis gave several insights on the dynamics of software aging. First, so we can estimate the unavailability of the system by steady-state solution of the CTMC. The steady-state unavailability of the system is explicitly given by the function of those transition rates. Second, by conducting the sensitivity analysis on those parameters, so we can discuss what is the best rejuvenation rate to minimize the system unavailability. So that was the result. So the power of CTMC for software rejuvenation system. However, so one of the significant limitations of this type of CTMC is the assumption of exponentially distributed transition times. So in the original model, all the state transition times are assumed to be exponentially distributed. So the limitation was addressed in the following studies. Doi, Poposteyanova, and Trivedi used the semi-Markov process, SMP, so that is used to model the time-based software rejuvenation system. So this model is presented in the figure. So you can see that this state transition is quite similar to the original model. However, now state transition is not limited to exponentially distributed. in particular from state 1 to state 3, so which represents the software rejuvenation transition. So this model, here we assume that it is a deterministic time transition. So which represents rejuvenation is triggered at a fixed time interval, time-based software rejuvenation. An interesting conclusion derived from the analysis of the SMP that there is a unique, finite, optimal rejuvenation time interval that maximizes the system availability under specific condition. So many following studies used SMP to drive the optimal rejuvenation interval in time-based software rejuvenation systems. Another extension is delivered by the studies used non-homogeneous Markov chain. Markov chain usually requires that the state transition time is not time-dependent. However, non-homogeneous Markov chain allows time-dependent state transition rate. One example study is conducted by Bao, Sun, and Trivedi. So they use the non-homogeneous Markov chain to represent the memory leak process. So the memory leak process goes gradually, progresses, so that gradual degradation is modeled by non-homogeneous Markov chain. Another example is the study conducted by GAG, Priafit, Terek, and Trivedi. So they used non-homogeneous CTMC to capture the transaction state of the system. So the model is presented here. So in this model, the state level represents the number of transactions in the system. So this model assumes that transaction arrives in Poisson arrival with constant arrival rate lambda. However, service time and failure transition is not exponentially distributed. It's time dependent. So this kind of system transition can be captured by non-homogeneous Markov chains. So now that the question is how realistic this optimal rejuvenation model. So there was an innovative study given by Vaidyanathan and Trivedi. So they presented a method to combine the analytical model with statistical models. So the statistical model was constructed from real empirical data. So to do this end, so they use clustering method to construct a statistical model of the system states from system measurement data, such as memory usage, CPU usage, CPU utilization, and so on. And then, so the SMP statistical model is combined with a higher level SMP model. That is another SMP and used to derive the optimal rejuvenation interval. So for another application of SMP, so it can be used to compute the job completion time performance affected by software rejuvenation. Machida, Nicola, and Trivedi computed the job completion time distribution using SMP. The system they considered is a virtualized system, so in which a virtual machine is running on a server. So the system affected by VM rejuvenation, VMM rejuvenation. So depending on the rejuvenation types, the preemption type is different, but that different preemption type can be considered in the job completion time analysis on SMP. So using SMP, so we can compute steady state availability as well as job completion time performance. Now, so let us go back to the origin and look at another thread of modeling studies, that is stochastic Petri-nets. So hereafter we call SPN. So SPN is also a category of a state space model that gives a higher representation capabilities. The model constructed by SPNs essentially can be transformed into Markov chain models. And the initial application of SNP for software rejuvenation is given by Gag, Priofit, Trek, and Trivedi. So they developed a Markov regenerative stochastic Petri-net, MRSPN, to model time-based software rejuvenation system. So in this SPN, it includes one deterministic transition. So the resulting Markov model is a kind of Markov regenerative process. So by analyzing Markov regenerative process, so we can derive the optimum rejuvenation time interval. So further complicated system can be modeled by fluid stochastic Petri-net. That is another variant of stochastic Petri-net. The study was conducted by Bobbio et al. So they tried to capture more complex system employing software rejuvenation, checkpointing, and self-restoration. So the more stochastic pattern has expression capabilities, the more we can model complex systems. So far, all the model discussed in the presentation is single node system. However, many real systems consist of multiple nodes, such as cluster system. So to represent the state transition of such cluster system, stochastic reward nets, so that is another variant of stochastic Petri-net, give a powerful solution. SRN allows us to represent complex system dependencies and to compute more advanced performance measures, such as performability. So this is an example of application of SRN to capture the state transition of cluster system. So SRNs were also applied for modeling the software rejuvenation system using server virtualization. Machida, Kim, and Trivedi used SRN to compute the rejuvenation techniques for server virtual system. So in this study, three different rejuvenation techniques are investigated, which are cold VM rejuvenation, warm VM rejuvenation, and migrate VM rejuvenation. So the expressive power of SRN enables us to model the complex state transition of server virtual system. So it is one of the hot topics to apply software rejuvenation to cloud computing system. So cloud computing system consists of various components, including hardware devices and software components. So in order to capture such a large-scale system, a hierarchical modeling approach can be used. So this hierarchical model combines a reliability block diagram, so which represents a higher level of structure of the system, and a deterministic stochastic pattern, which captures a detailed state transition of the component of the system. So since the book chapter covers our studies until 2050, so here we'd like to comment some recent advances in this research field. For Markov models, there are some studies focusing on software rejuvenation in Android mobile phones. So considering mobile phones, so one of the important measures we need to consider is user-affected performance. So such kind of measure can be analyzed using simple CTMC. So such kind of studies are recently presented. So another interesting measure is interval reliability. So usually we consider steady state availability, but so there's another work to consider interval reliability. So using some variant of Markov models. So for Petri-nets, so usually they are used for representing a larger scale system. So recently, different VM migration methods for software rejuvenation in cloud system was investigated. So they use stochastic Petri-net, and workload variation in VM migration process was also modeled with a stochastic reward net. So it is not exhaustive, but recently there are many studies focusing on software rejuvenation in virtual system and cloud system. So we had quickly went through the evolution of Markov models and the stochastic Petri-nets for software rejuvenation systems. Now, what will be the next challenges? For Markov models, so it will be used to analyze the effectiveness of new approaches to counteract software aging problems. Software rejuvenation is not only one solution. There could be another solution to counteract software aging. The effectiveness of new approach can be analyzed using Markov models. So Markov models, another application is to estimate the new measures affected by software rejuvenation. So one of the interesting measures is user-affected measure in mobile phone, mobile terminals, and maybe so interval reliability, extension of interval reliability, such kind of things. For Petri-nets, so it will be used to capture the system dynamics of larger scale system with software rejuvenation. And also it is interesting future direction to consider the application of software rejuvenation in other emerging computing domains, such as software-defined infrastructure, network function virtualization, edge, and fog computing, machine learning systems, and so on. So let me conclude my presentation. So we reviewed the studies of Markov chains and Petri-nets for software rejuvenation systems. So Markov chain and Petri-nets are powerful tools to analyze the dynamics of effectiveness of software rejuvenation. So Markov model is relatively simple, but it is useful to understand the essence of dynamics and effective measures. Meanwhile, stochastic Petri-net allows us to model larger scale system and more complex system that can be applied for other emerging computing domain. So we believe that these two threads of studies will continue the development in a complementary manner. So that concludes my presentation. Thank you for listening.